Alright, this is my lab 5 looking at Faraday's law and mechanics with magnets and induced current. So in the table of contents, we have our introduction, data and observation, experiment, discussion, and conclusion. For introduction, the overall purpose of this experiment was to observe Faraday's law and compare how long it takes a magnet to fall through a tube with induced fields. Comparatively, a magnet falling in free space will usually not have any sort of influence on it, but a magnet falling through an aluminum tube would induce a non-Coulomb electric field onto the aluminum foil, which would cause influences in timing. Fundamental principles here at play are Newton's second law of motion, force equals mass times acceleration, Faraday's law, and then Biot-Savart law, which talks about induction of magnetic fields. And then for a preview of the results, the larger the value of the magnetic dipole moment, mu, the more the tube will change in current. So for the introduction, the system was the magnet and foil, since these were directly involved in the experiments, while the surroundings were gravity. So for the experiment, the setup, you were to drop a magnet through an aluminum foil tube while recording with a smartphone, and then using this, you can monitor speeds of the magnet falling through the tube by taking the timestamps and then subtracting them in order to find the approximate time it took the magnet to fall through the aluminum tube. For data and initial observation, the length of the tube was 0.45 meters, the width of the foil was 0.2 meters, the magnet's mass was 0.37 kilograms, the radius was 0.18 meters. The magnetic dipole moment, as calculated in Lab 3, was 1.33 am squared, and the average fall time was about 2.3 seconds. So looking at the code, this first section of code was the code used in order to calculate the magnetic dipole moment of the magnet. And then the code below is looking at calculating the total flux between the magnet and the aluminum foil tube. And then this could be used in tandem with Newton's second law of force and acceleration in order to make our velocity and position update equations in order to find out where the magnet would be as time goes on per second. So in the simulation, we can look at how the magnet falls through the tube and the speed at which it falls through the tube. So this was the model. Overall velocity would increase, and then it would hit a point where it would not go past. It would be constant for a little bit, and then it would slow down as it exited the tube. And as far as the simulation goes, the simulation had a similar fall time compared to the recorded fall time I found in the experiment. And regardless of which direction the magnet fell from, the current induced in the aluminum foil would have been counterclockwise. So potential sources of error at play could be potential fluctuations in timing, using incorrect timestamps to tell when the magnet entered and exited the tube as far as the tangible experiment goes, and then precision of calculations for sig figs and rounding. So what if the resistance was totally zero, for the magnet to fall at the same time with resistance being zero, there would have to be some sort of magnetic influence between the aluminum and the magnet, or the electric field induced into the aluminum foil would have to be greater, and this would alter the magnetic fields, or the magnet's ability to fall, since induced magnetic field would pull it in the opposite direction to gravity. And if the aluminum foil had holes in it, then holes would cause the induced magnetic field to overall decrease, and the magnet would overall fall faster.